Following problem is number 40 on page 167, and it gives a scenario of a cold wire which for it to compress it requires a force, which in the force is given in F equals Bs cubed, and it's asking to find B and include the units, and we're given the length of the spring, the mass attached on the spring, and then the final length of the spring once it's stretched. So to find B, the first thing I do is I drew a diagram to see what forces were acting on it. Since the ball is suspended, gravity is going to be acting on it, so our net force is just gravity. So net F equals mg, and then the equation was F equals Bs. Since we know the net force is just mg, we can just solve for B by doing B equals mg over s. And I got the answer of force. I got the answer over here, which is 2,756.25 newtons per meter cubed. So I thought this was it was a very big number, so I made sure. So in the original equation, if we do m times u, we get 0.1764 newtons. So if you go back and plug this into the original, we should get a force of the same number. And as you can see here, the spring stiffness times the change in S cubed cancels the units, which gives us the force of 0.764 newtons. The units on the B was newtons per meters cubed because the S was cubed in the original equation, and the S represented the change in distance of the spring, so the compression or how far it's stretched. The second part of this equation was asking from which of the following were needed for an analysis of part A: the momentum principle, the fact that gravitation force acting on near the object is mg, the law of ordinary spring F equals ks times s, the rate of change in momentum being 0. So I said it was the force of law of spring where F equals ks times s. It mimics a lot like Hooke's law, which was, see, if you look at the equation closely, they both have forces. The B I assume to be spring stiffness, and then the S is just the compression or the stretch of the spring. Lastly, it gave us a scenario if you take the mass and you throw it straight down, releasing it when the length of the device is 33 centimeters, and then and the speed of the mass is 5 meters per second after a very short time, what is the stretch of this device, and what was the change in speed of the mass? So I drew a diagram of what was exactly happening. So we're basically taking the mass and we're throwing it down in the same direction as it's being stretched. So I said my net force was Bs cubed minus mg. Because we're applying an unknown force of F in the same direction of gravity, I said it was going to be we subtracted it. Otherwise, it would just continuously speed up. There has to be a force resisting it. So and the only force that I thought was F equals Bs. So to solve it, I did the momentum principle, which was right here, and then I simplified it down to where it was eventually delta V equals F net delta T over M. So after I plugged in, I got delta V as a very, very small number. And then V final was actually the V initial plus the change in delta V. The reason why it's not is this way is because the original scenario was negative 5 meters per second and it was going in the negative direction. So the final was V initial plus the change in V, which gives us a negative number. And this makes sense because as soon as it crosses that time, it's gonna slow down. It should be less than negative 5 meters per second. Because the spring is eventually gonna want to come back up to its original length. And to find the distance, to find delta y, I used I found V average by doing VI plus VF, and I found the change in y by multiplying V average by the time interval, which was 2.5023 times 10 to negative 4 meters per meters. All right, so that's good. Thank you.